Hi, welcome to Module 2, Supervised Learning with Feedback. In this module, we are going to build up on what we learned with Module 1 and embed supervised neural network into the feedback loop for a slightly more sophisticated tuning task than the one we covered in Module 1. Specifically, we are going to look at something called charge tuning today. I am going to explain a little bit later exactly what I mean by that. We are going to then formulate a charge tuning problem as a supervised neural network with feedback. Then we are going to cover some application to real-life experiments as we did in Module 1. And you are going to finish with coding demo with Tanko, where again, you will write your own tuning routine in PyTorch on some data sets that we prepared for you. So, just a quick recap. In Module 1, we learned that classifying a regime the quantum dot is in, single dot, double dot, is just a simple two-class supervised neural network learning task. Now we are going to move on something called charge tuning. If we found the correct regime, for example, we want to be in a double dot regime, the next natural thing you want to do is to prepare specific charge states. You may know from your quantum dot course that these charge states can serve as a really useful basis for a quantum computing, but they can also just be a goal in itself. You want to prepare some very specific state that you want to study later or anything like that. So what are the charge states? We learned in Module 1 that each transition in a charge stability diagram corresponds to the electron increase either in a left or a right dot. So by transiting this line, we increased from the state 0, 0 to the state 1, 0. And then if I transition on both vertical and horizontal, I will go to the state 1, 1. And I could continue. This one is 2, 2, this one is 3, 3, and so on and so forth. So usually if you have your dot pre-tuned, the next step you want to do is prepare some of these specific charge states and then do whichever experiment you are interested in. Of course, what you could do is to just measure perfect charge stability diagram like this one and count the transitions manually. Here, the resolution is high, they are super beautifully visible, so nothing stops you just to look at it with the human eye, count the transitions, map the corresponding voltages on the axis and be done. But again, collecting this beautiful high-resolution charge stability diagram is a lot of measurement time and a lot of work. So we ideally would want to avoid measuring all of this because if I want to prepare state 1, 1, most of what you see in this plot, those are useless measurement points that take a long time to collect. So I would want to just measure a small part of it and then decide where to move to converge on the exact charge state that I want to prepare. So what is the minimal experimental implementation of this type of task? That's the question that we are going to answer in this module.